Eleanor Dunn from the Dublin Institute for Advanced Studies.
Okay, hello everyone. My project is 4.1 on ground motion and unrest triggering on volcanoes. So my project is understanding how we can look at dynamic triggering and understand the stress and strain of volcanoes and use that to understand ground motion. So the volcano that I'm looking at first is Sierra Negra. It is on the Galapagos Islands, just west of Ecuador. It's a basaltic shield volcano, 1,100 meters high, and it has a unique trapdoor fault system. So this trapdoor fault system basically operates on a hinge. This can be seen in this plot here, where there are no earthquakes happening along this part of the caldera, and that's because where the hinge is, so it's stationary. And this trapdoor fault basically moves up and down. So its eruption history, it erupted in 2005 and then 2018. So between 2005 and 2018, it experienced about 6 meters of uplift. And then immediately following its 2018 eruption, it experienced about 8 meters of subsidence. And then very quickly following that eruption, it experienced uplift again. So it has quite a unique cycle of inflation and deflation, and I'm going to try and use that to understand how dynamic triggering is perhaps influenced by that. So what exactly, I'll just briefly mention what dynamic triggering is. So that is when you have the teleseismic events which travel and then cause some sort of triggered response at, in this case, Sierra Negra. Sierra Negra, we have one actively streaming station, which is just on the caldera rim, so it's quite convenient. And we did have several other stations which were collected in December. They couldn't be collected earlier because of COVID. And Sierra Negra is quite a difficult volcano to get to. But anyway, so the first just kind of case study I'll just show briefly is a Mexican earthquake, which happened in 2017, about 11 months before the 2018 eruption. And then this top plot you can see is a very low frequency, about 0.03 to 0.5. And this is the arrival of that teleseismic wave at VCH1 on Sierra Negra. And then if you look at the high frequencies of this is above 4 hertz, you can see that there seems to be some sort of triggered response. So when you get that P wave arrival, you then get the triggering events seem to happen. And then there are some, when we're looking at different triggered responses, there seems to be quite some unique features. So for instance here, there are these equally spaced triggered responses, and then if you compare that to the lower frequency, it looks like it could potentially be some sort of resonance going on. So that is something that I need to look into a bit more. But the problem with this kind of data set is that you need those large earthquakes to happen to actually be able to look to see if there is a triggered response. So the data set we have isn't huge because there haven't been that many large earthquakes that have caused some sort of triggered response. So I then used an STA over LTA algorithm to try and make sure that I could detect the triggered events when they were happening. So this is just for events before the 2018 eruption. There's about 10 events before that have been monitored before the 2018 eruption that seem to cause some sort of triggered response. And as you can see, the detection algorithm works pretty well. Because there isn't such a large data set, I'm able to manually compare as well, just to make sure it is working. And it does seem to detect those triggered responses quite well. So another part of my methodology is looking at dynamic strain. So this is to try and understand the stress and strain relationship on Sierra Negra, in this instance, when it comes to dynamic triggering. So dynamic strain, to calculate this, I've just used the magnitude of the velocities of all three components over c, which is the seismic wave propagation speed of the incoming surface wave. So when looking at this dynamic strain, so this top plot is just an hour of time, and as you can see, the first dashed blue line is the P wave arrival, and then the dark blue line is the S wave arrival. And following those arrivals, there is some steep increase in the dynamic strain before it then returns to what you may class as normal levels. And then if I zoom into this time period, following that initial increase, you then get the first triggered event, and then following that S wave, you then get the remaining triggered events, and it remains at that high level until it then returns to normal. And this is a very similar case with the other triggered events that I've looked at. So yeah, this is, I want to hopefully end up using this to understand kind of the relationship of stress and strain on Sierra Negra, and if it can be used as a stress gauge, and then how this relates to its inflation and deflation cycle during its eruptions. So again, it seems to be gearing up for another eruption, maybe not for a few years, but yes, it would be good to kind of see how that impacts the dynamic triggered events again. And then another thing I would like to look at is the minimum dynamic strain that's required for any triggering event to go ahead. So in this case, it would be just before the first triggered event happens, and how that compares to other responses. So just what's next? So obviously, with any research, you want to improve the statistical confidence to make sure these are definitely triggered events and just not local seismicity. And then I want to plot these triggered events and how that is impacted, once again, by the inflation and deflation cycle. And then the importance of dynamic strain in relation to the stress state. And then finally, I want to apply all of this methodology to other volcanic locations of interest. Some ideas that I've got in mind is Hekla in Iceland and Mount Etna in Italy, and this is because DIAS has stations there, so it would be easy to apply this methodology to the data that we've collected. Thank you.